All right, let's start with this webinar. Thank you, everybody, for joining us today. Very excited to show you how we have collaborated with Thales Alenia Space at Cognitive Design Systems to use our software Cognitive Design to show potential to streamline the engineering process for an entire bracket family for this space application. All right, so I'll let Florent introduce himself.
Yes. So hello everyone. Thanks to participate to this webinar. So just to quickly introduce myself. So I work for Thales Alenia Space in the Toulouse entity, where we mainly design, produce, and test a payload for our satellites. In telecommunication payload, we need antenna, and so for this product, I'm in charge of the management of technologies development. So in terms of technology, we talk about composite materials, aluminium, titanium, invar metals used on our products, also thermal insulation technology, metal coating, and also additive layer manufacturing. And the topic we will discuss today is linked with this topic, this technology.
Thank you, Florent. And myself, I am Alejandro Carcel Lopez. I am the Director of Engineering at CDS. I'm also an aerospace engineer, and I've been working in aerospace and in the innovation space for over 9 years. All right, so let's have a look at the agenda for today. First, we're going to quickly introduce both CDS and Thales Alenia Space and Florent's division. Then we will have an understanding of the use case that brings us today together. We're going to look at the problems or the challenges faced by Thales Alenia Space with antenna tripod family. And then we will jump to how we can rethink the process with cognitive design. Once we have a good understanding of the process, we will give you all a good deep dive into the software, the workflows, and how things work, and so you get a good feeling of the details of the workflows and the value that we can achieve with them. And then we will wrap it up with the conclusion of this study, and then we will have about 15 to 20 minutes of Q&A. All right, so let me introduce you to CDS. We are a Toulouse, south of France startup. We were established in 2021 by 3 co-founders that today has grown into a team of 20 people. We have some funding. We do a lot of engineering projects and also the software sales, which is the core business model of our company, but also to increase the amount of team members. We raised 2 million in 2023. We've worked with more than 60 clients around the world, mostly based in APAC, EMEA, and America. You can see some of our partners there on the right. So there's Thales Alenia Space and many others that will look familiar to you. And at CDS, our vision is to really transform the way we do engineering. And as our CEO, Rushik Madroja, says, into a cognitive creation. So we want to make the engineering process somewhere where we integrate design insights, manufacturing insights, performance insights, cost insights, simulation. So we really want to break engineering silos for good. Sustainability is an important topic for us as well. And that's why we want to help accelerate sustainable design and have those sustainability metrics in the design process. And we incorporate AI where it makes sense to accelerate the design process and the design decision-making process. So lots of automations that happen in our software are powered with AI with the right purpose. To give you better insight into our technology, So one differentiating factor is we master implicit modeling. In our software, all of the modifications are done with this geometry kernel, which is different from traditional kernels like brep. We basically describe the geometry with implicit functions, which is a way to be able to modify the geometry based on data and in a very robust way without breaking it. And this also allows us to work with highly complex geometry, highly organic geometry, without breaking it or without running into issues when doing iterations or automations. We use AI-driven analytics to help the engineers make the best decisions in their design process. For example, if you're trying different lightweighting methods for performance, if you're analyzing the implications in cost, in manufacturability of your design decisions, the materials that you choose, depending on your business case, on the cadence of production, on other data based on your context, on your location, for example. You can analyze all of that, and with AI, we can accelerate the right combination of parameters to find the best part that corresponds best to the objectives that you're looking for. It may be reducing the cost, increasing performance, reducing weight, increasing manufacturability, and along, etc. In order to create this analysis, we create parametric design workflows that allow you to test different strategies and also to reuse this engineering knowledge later across a whole family of parts. And that's precisely the point of one of the big points of today's webinar. We're going to see how, with the workflows that we create in cognitive design, we are able to capture engineering intent, engineering know-how, and reuse it on different geometry to accelerate design process. Together, we are conceiving a platform where we accelerate scale engineering in an intelligent manner. We allow engineering teams to explore more options faster and to ensure that these options are aligned with the project management constraints. Also, today I have a big announcement. We have released our software Cognitive Design 2.0. Basically, you will see it today in action, how you can explore many different opportunities in the design process, identify with confidence the best design direction, and make modifications and reuse the workflow in an agile manner across the whole family of parts. So the two pillars here are the design exploration capability and the design automation capability. I'll hand it over to Florent to present Thales Alenia Space.
Yes. So my introduction of Thales Alenia Space will be quite short because I imagine that you know well this company. Thales Alenia Space is the global organization with a powerful footprint in many European countries. We are about 8,000 employees, and we are present in 7 countries in Europe. As illustrated on this picture, Thales Alenia Space, not just the previous one, sorry, address a large scope of business from telecommunication, observation, up to exploration. With the next slide, I'm converging on the topic we will discuss today. For the satellites that TAS design, manufactures, and test, we use additive manufacturing to produce a growing number of technical parts. And these components, mainly printed in titanium and aluminum using powder bed technology, include the structural parts as illustrated on this picture and RF components on the next picture, next slide. And sometimes we combine both functions. The main reason for using additive manufacturing for this kind of components is obviously the mass saving and the improvement of the technical performance of the parts, or reach new range a new range of performance offered by new design opportunities. And ideally, to obtain this status without any additional cost in the design phase. On the next slide, I will introduce the study case we will discuss today. So the design activities of these 3D printed parts illustrated before remains a critical step for us and for everybody, imagine, with respect to technical performance, printability, and part cost. So we are therefore working to adapt our design tools to optimize this critical design phase. The main objective or main goal is to optimize the ratio design cost versus final technical performance. And so a few months ago, we were interested in the tools proposed by CDS. And so in this way, we proposed to CDS to work on a study case illustrated on this slide. So we are talking about little tripods, so it's little fittings like this one. I hope you can see it, yes, in titanium. It's not a complicated part. It's based on a design that is optimized for 3D printing and not really optimized also in terms of mass and stiffness ratio. In fact, it's for us a legacy design we have never challenged. It makes the job, but there is potential to optimize it in terms of mass, stiffness, and also printability. The problem is that generally, when you want to optimize the mechanical behavior, you imagine to consider organic design. But organic design means also generally huge design cost. And it could be a problem when you are applying that on many parts with specific interfaces. And it's typically exactly what we have on this use case. In fact, on these little tripods, these tripods are fixed on the reflector, so a sandwich technology. And the problem is that all tripods are specific. All interfaces are different from one tripod to one other. And so this makes quite difficult to imagine to adopt organic design and to consider topology optimization specifically for all these single parts, considering the fact that there is no future production. In fact, one reflector means 4 individual singular tripods, and it will be the same for all reflectors we will produce in Thales. So the challenge today is to be able to obtain, with no additional engineering cost, tripods designed better optimized for their mechanical functions. Tripod easier to print also. The design is quite simple, but not so easy to print. And to obtain this improvement for parts whose environment and mechanical interfaces vary from one part to one other. And so this is the challenge we have proposed to CDS to address.
Thank you, Florent. Very clear presentation of the use case. And just to kind of summarize it on our side, right? So the estimation is that there's about 80 variants needed per year. And as Florent mentioned, there's going to be quite some time going into each variant, and that leaves little time for innovation or optimization of each one of the variants. The current design methodology for the tripod family, basically every time we have a new part, we have requirements, we have to do the CAD, we have to do the simulation, the manufacturability, the business feasibility for each one of the different components. And then every time we change the design based on the new requirements, we need to start all over again. So just by the length of this process, this means that we never have the chance to really innovate or make an optimization. So this is where we came in with the objective of building one reusable workflow that allows Thales Alenia Space engineers to make decisions for each part what is the best technology. It could be additive manufacturing, or perhaps even considering CNC machining in a more optimized manner could make sense. Aluminium versus titanium. Maybe titanium is not always necessary, and aluminium can be more interesting. So this cost, performance, and manufacturing trade-off is something that we're looking to tackle. So at the same time, we need this workflow to be reusable, right? We have more than 80 variants per year, so we really need to very fast get to these decisions, so that the process is sustainable and we can become more competitive in terms of the weight and the optimization of the part. So we had a clear target. We needed to have a process that is much faster, that is automatable for different variants, for all the 80 variants that Thales Alenia Space is trying to optimize every year. And we had a reference design. We wanted to achieve less than 250 grams per tripod. And of course, we had to at least be equally good in terms of stiffness, and also to have a safety factor big enough for the space standards. Looking a bit more in detail into the engineering constraints, so we are going to have the payload forces on the bracket. You can see the design space there, and where we're going to restrain it. So basically, we're trying to optimize the legs, the leg geometry that connects the payload to the fixed regions. And you can see, based on the constraint, we have some no-go areas. So the design space is not fully solid inside, but it's quite constrained in terms of where material can go. So we can consider titanium, additive manufacturing and machining, aluminum as well. And yeah, we will print this part based on the legs in the air. And the loads that we consider for this part are 1500 Newton in XYZ. Okay, so now that we understand the use case brought to CDS by Thales Alenia Space, we're going to dive a bit deeper into the cognitive design approach. So as we just saw, today is a linear process for every part, where every time we start from the requirements and we end up with the final part. And the estimation is that every time we do this exercise with a legacy workflow, this takes about 2 weeks. So 2 weeks every single time, and we end up with a part that is not fully optimized. The way we rethought this workflow with cognitive design is we're going to build one single reusable workflow that can be used for each set of requirements. Every time we'll have the option to do a full-on design exploration for each one of these set of requirements, and then design fine-tuning based on simulation, based on manufacturing data, cost data. And then we will be able to export the geometry for validation. So this allows us to reduce the process time for every part. Part number one, you can see that it takes also 2 weeks, is the time to set up the engineering workflow, the design exploration process, and make sure that everything, all the sophistication we need in the workflow is included in there, and that everything is working correctly. But then once we have this reusable workflow, every other part will only be a couple of days that we will need to take it from the requirements until the validation. And as you will witness later, the reusable workflow in cognitive design is actually quite fast. And just in a few minutes, we can get a fully optimized part for a specific manufacturing technology. But we still consider that the whole process for each part takes up to 2 days because of more advanced validation loops with thermoelastic and model considerations. All right, so let's have a deeper look into the project. So the first stage is we're going to build the workflow as we mentioned. This is the work that can take about 2 weeks, sometimes less, depending on the expertise in the software. But basically, in this workflow, we set up a design space, which we can create automatically based on the legacy design as well, or it can be brought from CAD software. And then we will generate topology optimization or perhaps a different generative design method. At CDS, we use topology optimization level set, but we also have developed new methods such as topology weaving or topological enclosure. Once we have decided the best optimization strategy, we will refine the design with simulation results and with manufacturing analysis results. So we will use simulation-driven design, manufacturing-driven design in order to refine and fine-tune the geometry. And then we will connect it to our design explorer, where we will obtain KPIs such as performance, feasibility, cost. And now we have a workflow where we can create tons of variations based on these different optimization methods that I just mentioned. Topology optimization, you can generate many designs based on topology optimization parameters. Perhaps you want to do topology weaving. Perhaps you want to do lattice structures inside, shelling, variable shelling, etc. So there's so many options, and it's hard to know ahead of time which one is going to be the best one. It may depend on the application, or it may be different for each part each time. Also, you have the question of manufacturing method and materials. So in the end, you end up having so many design variations, and it can be quite overwhelming. So that's why we have created the Design Explorer. So it's very easy for the mechanical engineer, the design engineer, or the simulation engineer to make decisions based on all of these possibilities. And then once we have identified the best methods for this type of part, the good thing here is we don't have a black box approach where some machine just created these designs and proposed them to me, and I don't know much about the design at the end of the day, how it was generated. We have a full transparent box approach where the best design method, the best design workflow, we can actually reuse it completely transparently, and we can have full access to the data that was used to generate that specific design, all of the modifications based on generative design methods and data-driven design decisions. Finally, the other point was to be able to reuse the workflow. So we have, based on one part on a whole design exploration, we had identified the best way to do these designs, and now I want to use it on a different part. So you will see today how once we have selected the best workflow, we can plug in a different part and in a few minutes get a new optimization that is ready for manufacturing and for which we know all of the KPIs linked to it. Okay, so now we're going to dive a bit deeper into the cognitive design workflow details. So let's start with the workflow build-up part. Here's the full workflow in cognitive design. You see that there's different stages for topology optimization, the geometry post-processing, the manufacturing-driven design, simulation-driven design. You have the manufacturing cost and CO2 analysis. So at the beginning of the workflow, we're going to import the CAD data. In this case, it was the legacy design and also design space. And we will be able to create a whole finite element assembly setup. Here we can define the material, we can define the different load cases, the different surface loads that are going to be applied. So you can see they're applied in the 3 different directions, the 1500 Newton load, the 3 load cases, all of them together in the scenario and in the plug to the solution, where we are going to define parameters such as the precision of the FEA model. And then we launch the topology optimization based on different parameters: volume fraction, refinement level, and other level set parameters such as the strength. Then you can observe the optimization process and how material is being removed, volume fraction reaching the 8% of the design space in this case. So at each iteration, compliance gets more and more minimized, as you can see here as well. And then once the compliance has been minimized and the volume fraction has been reached, we have our topology optimization. Level set allows for smoothing, automated smoothing, but sometimes for very fine topology optimizations, we might not use smoothing. And in those cases, we can automatically reconstruct the topology optimization by joining it with the functional regions and by smoothing all of the raw areas of the topology optimization result, and also making sure that all of it stays connected together. Then we can quickly run a meshless FEA analysis. So we don't need to be creating a tetrahedral mesh every time. It's a fully automated process where every time we can get a performance metric on the design. So here we can see for the three different load cases, what are the stress areas and what are the stress values. So the next step is going to refine the topology optimization based on this data. We're going to use simulation-driven design. We have different options for simulation-driven design. In this case, we're interested in increasing wall thickness in the high stress areas to reduce stress levels, but by adding very little weight to the topology optimization. You can see here how that area with higher stress was solidified and thickened further. And then we will take our geometry to the manufacturing-driven design. In this specific case, we guarantee that the minimum thickness for the process is met, 0.8 millimeters. And also we're making sure that we have no issues with bulk volume, so that we don't have thermal concentration. So once our part has been optimized with a generative design method like topology optimization, with simulation-driven design, with manufacturing-driven design, and our geometry is clean and smooth and integrated with everything, we do the final FEA analysis. So in this specific case, when we compare before simulation-driven design and after simulation-driven design, we see that our maximum stress value has gone from 97.4 megapascal to 76 megapascal. So now we can look at other things like the manufacturability, the cost, and the CO2 emissions. So we have different macro blocks that we can create and store in our library to reuse each time. You see that we have aluminum CNC, aluminum additive manufacturing, titanium, also for both of them. So each one of these blocks has fully customizable parameters when it comes to the manufacturing analysis, to the cost analysis, the CO2 analysis. So for manufacturing analysis, we can adjust the minimum thickness in the process, the overhang angle, the volume threshold, and also things like slash area variation. And it will also analyze other issues such as internal cavities. For the cost, we will have access to what manufacturing technology, quantity of parts, hourly rate of the machine, machine cost, and recurring and non-recurring costs. For the CO2 analysis, you will have access to machine power consumption, material-specific energy emissions. So you can fine-tune all of your parameters. And then once you are done with the whole workflow, you can create a reporting on this specific part based on simulation metrics, manufacturing metrics, cost, and CO2 metrics, and send it to your Design Explorer. So here's the Design Explorer. Here's the design that we generated there. And we will want to compare it to the reference design, the original design, which you can see there. So we can set it as a reference. And now each one of the different designs generated, which you can see there in terms of mass, safety factor, stress, displacement, etc., will be compared. We will get a quick comparison to the reference. We will have full access to cost. You can see this part specifically is in the 1,100 euros. Also the carbon footprint, what material we use, what process we used, and all of the manufacturing constraints. You can see that we can play with the graph. We can put, for example, the x-axis is part cost and the y-axis is maximum stress. So we can easily compare all of the different designs and select the one that is the most interesting. So let's have a deeper look at the Design Explorer. So you can see here the different designs that we generated. You can see the manufacturing analysis also. And you get a manufacturability score. So we can very quickly also compare the different parts if we are having any manufacturing risks or difficulties. So for the project with Thales Alenia Space, we explored many designs. And here you can see the ones that we retain as the most interesting ones. Here we can see we can filter by CO2 emissions, by safety factor, by part cost. Also, we have a heat map based on the stress values. So we can also see which ones, if there's a design that is too high or too low in stress, we can filter them out, as you can see. We can also apply filters based on the full range that we obtain for the parts. For example, here, I'm only interested in keeping all parts that are below 1,500 euros. And then only those options are presented to me. And I can see that the lowest weight is the design number 2. So that may be the one that is the most interesting. I could use any other filters simultaneously, like weight, CO2 emissions, safety factor. And then little by little, from a whole spectrum of possibilities, we can narrow down the solution to the one that best corresponds to our requirements. And then once I have made my analysis, I can export the geometry as a PDF or as a CSV file. So to give you a perspective on it, you can see here the report that has been generated by cognitive design with all of the different filters that have been applied, all of the different design iterations, and you can see all the detail about mass, safety factor, stress, displacement, cost, carbon footprint, what materials were used, some insights into the manufacturability analysis, and so on. So now we're getting to, I think, the most interesting part of the webinar, which is, okay, I'm quite happy with the design that I found for this specific application. We retain design number 2. And now I want to reuse this again for another part. So you see, we can click here on Insert Workflow button, and we will be able to put it all together in a new sub-project in cognitive design. And now I can come to the very beginning and insert a new geometry. You can see that we're changing the tripod live. We're changing the design space. And then we can reuse the whole workflow again. So we can either manually select faces like we're going to do in this example, or you could also import them if you have them available from CAD. Either way could be done. So we are selecting here the faces that are going to be restrained. And then we're going to select the faces that are going to be loaded for this new tripod. Then once you're done, you can validate your selection, and then you can start rerunning the workflow. You can either run it at the end and everything will be recomputed automatically, or you can go one by one. For example, in this case, I'm also changing the load case in the part. So I'm reducing it from 1500 newtons to 1000 newtons for this smaller bracket. And then you can run the topology optimization again. And you could as well explore different parameters if you'd like. So we launch it, and then the optimization process will start. So you can see here the optimization process. We accelerate the video a little bit for time purposes. You can see that we have obtained the new geometry that is considered optimized for this load case. So now, if you were to be normal CAD, you would need to transfer the topology extension to CAD and rebuild on top of it. And you see that we have some few disconnected regions and kind of rough looking regions. But with our geometry post-processing, which uses the implicit kernel for the smoothing and advanced functions for the reconnection with the functional regions, we can get a clean geometry at the end. And then we will do a first analysis on this topology optimization in order to obtain data on stiffness and also on stress values. You can see the von Mises stress map there. That was load case number 3. This is load case number 1. You see that we reach about 120 megapascal. So now we are going to plug the part into simulation-driven design. So we're going to, again, use the variable offset strategy. And then we will observe that the thicknesses have been modified based on the stress data. And then in manufacturing-driven design, in this case, why not? We can do a modification. Maybe we're considering machining, so we change from additive manufacturing to machining. And we're going to guarantee a certain minimum feature spacing and create a part that is manufacturable by machining. So you can see that we automatically created a geometry that is a lot more machining friendly than the pure topology optimization, which is a very complex organic shape. And then we can go ahead and run the final FEA analysis, and then we will take care of the manufacturing, the cost, and the CO2 analysis. Since we have changed the manufacturing method, instead of using the aluminum additive manufacturing library, we will use the aluminum CNC library. So we have our final FEA analysis done on the geometry. We have highly reduced the stress levels. You can see that we are in about 41 megapascal for load case 1, whereas at the beginning we were at 120. And then we do the final manufacturing analysis, which we can see here, and we can see the areas where we have higher risk based on the thickness, for example. You can see, you can calculate the cost and the CO2 analysis, and then you can create a new Design Explorer iteration. You save it, open the Design Explorer, and there's our design. So in this process, we manually added it to the Design Explorer, but in a very recent version coming up, we will have the ability to add all of the designs automatically as well. All right, so you've seen in detail the cognitive design workflow and how we reused it for a different tripod. So if we go to the original case, basically the best designs that we retain are the ones that you see on the screen. Each one of them has, compared to the reference, a different mass, a different stiffness, a different safety factor. The first thing that stays out is our topology optimization here, and with the simulation-driven design, manufacturing-driven design, has been able to highly outperform the original legacy design. All of these designs are much stiffer than the original tripod, and all of them, except for the design number 5, are quite lighter compared to the original design. And all of them have a safety factor above 1, even when we use very conservative hypotheses for the aluminum material in additive manufacturing, where we consider the yield strength to be only 70 megapascals. We can see the manufacturing metrics. Some of them are higher, some of them are lower. We can get an estimation of the cost of the part, and we can quickly compare which methods and which materials emit more carbon footprint. So, for example, you can see that machining has a higher carbon footprint than additive manufacturing. And design number two stood out as the one that, first of all, is the lightest one. It's also much stiffer, and the safety factor, even though it doesn't reach 1.5 based on the aluminum yield strength, it's very promising, and it's basically the one that would make the most sense for this case. So actually, the original legacy part was made in titanium, and with this study, we had identified that we actually can afford to change to aluminum while keeping a lot more stiffness and staying much lighter, 45% lighter. So to conclude, we have created a workflow where we can accelerate design decision-making process for the design thanks to the design exploration. We did fast trade-offs based on performance metrics, cost metrics, manufacturing metrics. The parts that we generated with these methods were overall lighter, stiffer, and they were highly manufacturable. And we witnessed how once we have built one workflow, we can very easily and highly automatically reuse it for a different part. It only took a few minutes, and then overall, in about 2 hours, with some fine tuning, we can get with a geometry that is ready for the validation and for the manufacturing. Thank you all for assisting today. Very happy to see that so many people were interested in this topic. I hope you found that interesting. And now, as promised, we have 15 minutes for questions. Okay, so let me see. The first question was by Martin 7 minutes ago. So the question is, can you do this optimization workflow for all kind of manufacturing technologies and materials, like sheet metal, design, injection molding, anisotropic material? So yes, we have manufacturing automated modifications for different technologies, and that includes injection molding, that includes die casting, that includes machining, forging. Also, we have the ability to define anisotropic, well, orthotropic materials with different properties in X, Y, Z directions. So yes, I think we can cover a high amount of the problems that you propose. So what was the safety factor? Nicolas was asking what was the safety factor on the legacy part and the cost. So based on our analysis here, the original safety factor was about 1.3, and the cost was in the 1,100 euros range. But this analysis might not be the exact one because that is a bit more confidential, but just to give you a comparative reference with respect to the other designs. Okay, we have some questions about what kind of optimization analysis can be done. So thank you, Raul, for your question. So today we can do static analysis, model analysis, and very soon we will also integrate thermomechanical analysis in the software. For CFD data, we can import data from CFD tools such as ANSYS Fluent or StarCCM to give a few examples. And we can actually do optimization based on things like thermal or velocity fields for the fluid. So Asia had a question about the manufacturability parameter. Yeah, so we do different manufacturing checks depending on the manufacturing technology. This can be linked to, for example, if we're talking about molding technology, draft angle analysis, thickness analysis, thickness control, filling time. So depending on the technology, we will have different analysis and we will identify how much manufacturing risk there is for each one of those analyses. And we will do an average we will get a manufacturing score out of the whole process. For structural analysis, what different types of constraints and loads can be applied? So we can cover most structural problems. We can cover, constraints for stress, constraints for compliance. Also, we have model analysis, and then we have the typical boundary conditions that you will have in FEA for modeling different ways of constraining parts, fully restrained or sliding, or you can also bring together different components and have load being transferred from one component to another. Okay, I think I have answered a few of those questions that I see in the chat. Maybe this one is for you, Florent. In this use case, the initial design was made through a classic CAD authoring tool, like CATIA, for example, and no use of implicit model.
Oh, sorry, the use case.
Yeah, so maybe yes. I think the question is about how was this originally designed before, if you can give more detail.
Yes, it was done using CATIA, yes, you're right. Only yes.
Okay, thanks. And then you were doing the back and forth with FEA analysis. Okay. So we have a question about if the software is used locally or if it's cloud-based. All of our software at CDS is on-premise, so nothing is in the cloud. Also, to clarify, the AI methods that we used in the software, they are all based on previous knowledge gathered by us, and also it'll stay anything that comes from your analysis. For example, when we use multi-objective optimization, all of that is based on the own data that you're generating in your workflow. We don't have a cloud where we collect your data and we reuse it in general, but everything is run locally and on premises. You have a question from Antonio Florent. What is your conclusion on the CDS solution? Is it immediately applicable in Thales Alenia Space engineering?
Yes, good question. In fact, right now we are still in assessment phase, to be honest. For us, the next step will be to assess this software directly in our design office in Thales, in order to learn more about the potential of this solution, and also how to integrate these new tools in our ecosystem of design, in terms of design tools and also mechanical sizing tools. So is it immediately applicable? Not directly, but based on this study, I think we can. I think that these results are promising, and that we can be optimistic in terms of delay to implement it in our design office. Yes.
And also linking to the next question, which is what are the output CAD formats for generative design? So we can export step from our software, and you can integrate that into your CAD assembly. Also, we have functions that allow you to get clean CAD with clean interfaces. So we understand that every engineering team has an existing digital tool chain, and it is a big focus for us to integrate the digital tool chain, both in terms of integration with CAD and also integration with other analysis tools in FEA. Yes, mesh file can also be exported. How do you incorporate the new model in your legacy system with CATIA and legacy PLM? So yeah, you can export the step file and you can integrate into your PLM without any issues. And I think we've covered most of the questions. So I think we can leave it here. It was very nice to have Thales Alenia Space with us, so that you can all witness what is possible with cognitive design and how we can apply to a real problem, a real challenge, and create value out of it and create new possibilities. So I hope you found it interesting. Please reach out to us. You have a QR code on the screen. You can contact us if you'd like to have a conversation with us and see how we could apply cognitive design to your own challenges, to your own business problems and engineering workflows. Also, Next is coming up. We will be there in Hall 12, booth D15. And actually, we will have these two tripods printed in our booth. So feel welcome to come and check them out and have a more detailed conversation. I see that there were some questions about the parameters in the manufacturing process and things like that, and the cost models. So we're happy to have a conversation with all of you and show you in more detail in a dedicated meeting. I'll let you some closing words, Florent, as well, before we wrap it up.
Well, it's okay. Thank you to all.
All right. Thank you, everyone, and see you next time. Bye-bye.
Thank you. Bye-bye.